This is a video that is a continuation of the previous tutorial. Here I will guide you what to do and what I do when I am classifying these light curves, so hopefully you'll get a better understanding and learn from this. If you have not watched the previous tutorial video and you have no idea what you're looking at, then I suggest watching that video before continuing on with this one. So let's begin. What we have here is what is known as a noisy light curve. This is probably the most common type of light curve that you'll see, where there is very little in terms of stereo availability, and if there are any transits, they're extremely difficult to tell them apart from the rest of the curve. Um, as you can see here, there are no visible transits or anything of interest to note other than this data gap, but it's not really important to note, so therefore we can press done and go right to the next curve. This is another noisy light curve. It's affected more by data gaps. It's a bit glitchy here. So again, we can press done. This is a more variable curve. Let's have a look. Right, so this concerns me for the rest of the curve. It's like this is definitely all glitched. There's a possible transit here, which I'm going to mark, and we can use the tools to zoom in, get a better look at it. It is definitely a transit-like event at the very least, so I'm going to keep that curve. The transit, I mean. Maybe this one? Because it's so close to the glitchy area, I'm not sure. What I'm going to do is I'm going to mark it. Mark that, but I'm not going to mention it when I'm done. So because I found a transit and it might be something looked into in the future, I'm going to press done and talk, put a note. So transit day 1, and I'm going to just give a note, possible glitch. The hashtags means it means it's a link that means every glitch can be more visible to researchers and other volunteers to show that this is a glitched curve. Yeah, so add the comment. There we go, and we go right back to classifying. Again, we've got another noisy curve. There's nothing that is outstanding here for me. No, so I'm going to press done. Now this is a much more variable curve. It's chaotic and its brightness changes very rapidly. So this is what is known as a irregular pulsating curve. These are typical of stars of greater than 5 solar radii, but are not always so. So let's check the info. Annoyingly, there's no data here about the solar radii, so we're going to have to go to ExoFop or Simbad to check it. The magnitude is the lowest I've seen in a while, so that interests me. So I'm going to press done and talk. So let's go to ExoFop. So this is the star. Looks like 32 Cephei or Iota Cephei. Yeah, Iota Cephei. It's a red giant star, so well, the orange giant star because K is orange. So what I'm going to do is you might mistake all these for transits, but it is just the variability of the curve. And it's unlikely this is a planet because we found that it's a red giant. Yeah, it's a quite close red giant as well. That probably explains the magnitude. So what I'm going to do is type the star. So iota Cephi. It's just one eye. And copy this Simbad link, and place it there. And also going to mention the magnitude. Low magnitude star. So people are going to be aware of what the star is when they look at this, and they'll be aware there's a low magnitude star. Oh, of course, K0. Just so they know what the star is. And add that comment. And let's go back to classifying. I've got another noisy curve. Again, no, nothing of note. Another noisy curve, but maybe that, but it doesn't look coherent enough to be a transit. No, I'm not going to mark that. Here though, looks like a promising one. The brightness is a bit of a concern. The massive degrees of brightness. So this is probably a small star, or it's either glitched, but looks more like a clump rather than a coherent transit. And this line doesn't convince me. There's all sorts of different measurements that are high in brightness over it, so I'm not convinced that that's a transit. Again, another noisy curve, but maybe. I'm going to mark this one, but I'm not confident enough that that's a transit to note down. So I'm going to press done. This is a very glitch curve, so I'm not going to take anything seriously in this one. You see the brightness just randomly just decreases out of nowhere, and the rest of the curve is noisy. So now we got some transits. So we got star with 0.7 radii. So this is a K type star. So we've got transit at around day 9, and it looks like day 21. Yeah, that's definitely a transit. And this one, yeah, it's good enough to be one as well. So off screen, I've calculated the radius, and it's roughly that of a Neptune-sized object. But it might be a simulated curve, but if it's not, I'm going to press done and talk. It is simulated. So it's good I didn't waste all that time. So there's another variable curve. it's a gradual variable curve, so this might be one. It might be good enough to mark, so I'm going to do that as such. Another noisy curve. I haven't found any eclipsing binaries yet, which is odd. Another noisy curve. You can see there's lots of noisy curves, especially this sector. Noisy. I think that's more of a glitch than a transit. Got another pulsating curve, looks of it. Yeah. It's chaotic. I'm not convinced there's any real transits here, even though they may seem as so. Ooh, this is interesting. So when you have a curve like this, these dots are indicators of solar flares. So these are most common with much smaller stars, such as red dwarfs. As you can see, this is a red dwarf. It's a very small one. But there's no, it's so, because of the flares, it's much harder to see if there's any possible transits. But I have a collection of flare events. So what I'm going to do is press done and talk, add it to the collection of flare events, and add it to flare, and also mention it's a red dwarf. Yep. Go straight back to the classifying. So another. I'm not convinced that this is a flare. Let's have a look. It's a sun-like star. But again, it's another noisy curve, and because there's only one of these dots, I'm not really sure if that's really a flare or just an error. So this looks promising here. So I'm going to zoom in to, it's there. Yeah, it's there. But as you can see, it's the readings are all over. It's not a convincing event. So I'm going to leave that as it is. And again, so this is a noisy curve that's slightly variable, but there's nothing that really outstands as being a possible transit. If we zoom in, yeah, there's nothing that's really outstanding for me, at least. So press done. Oh, this is a very glitch curve. You shouldn't be confused when you see things like this, because this is usually the result of either contamination or light scattering from the moon. This sector and I think 25 and 26 are also affected by light scattering. So these sorts of curves will be more common than we wish. So again, no transits obvious. It's another noisy curve. Again, nothing. No, nothing really. Now here we got an eclipsing binary. So one may mistake these for transits for two different objects, but this is the same object. Because it's so big, it produces an effect when it goes behind its star, and it manages to reduce the brightness of it to a not as massive as a normal transit event, but it still makes its a mark on the light curve. Um, so when these smaller transit events are known as secondary eclipses. Um, when you have a binary star, you were advised to also mark them as transits. So this is what I'm going to do. I mark all these transits here. And if an easy way to tell the difference between an eclipsing binary and um, a planetary transit, if these are sorts of events, these secondary eclipses are present. And as you can see, they are. So this possible object is not um, it's not a possible planet. So because it's an eclipsing binary, as you can see, someone's already marked it as such. And I'm also going to add it to my massive collection of eclipsing binaries and also make a comment. So I've also just went to Simbad and I found the um, star's name, well, its primary name, and it's already listed as the eclipsing binary, so it's already known to be as such. That's all I need for the comment, so that's what I'm going to put. Classify once again. So here is another obvious eclipsing binary. So again, just marking the transits as such. So this one is a much faster orbiting than much closer system than the previous one. Again, and because no one's commented on it, I'm going to also make a comment. Eclipsing binary. And this is the name of the object in Simbad, or the one that is pointed out. So I'm going to add a comment. Almost forgot to add it to the collection. Let's go again. So this is another eclipsing binary, though it may not seem so. Check the star size. So doing the radius calculation off screen, it's around 3.18 Jupiter radii. So this object is probably closer to that of a red dwarf star, maybe a large brown dwarf. And also another aid here is this small little dip here. This is the secondary eclipse of this. So because these two are so close together and there's no other like large transits in sight, it's likely that this is an eccentric eclipsing binary, so as an elliptical orbit. So someone's listed as a eclipsing binary. So I'm also going to put eccentric eclipsing binary, and there from Simbad got the name of the object that's most prominent and linked it, and the comment is made. Again, these are pulsations rather than transits, even though they look like there's tons of transits. They're all it's rapid pulsations. It's likely this star is quite big. As you can see, it's 10 solar radii. So these are not transits, unfortunately. And this is one more eclipsing binary, but it's on a variable curve, so it's to make some really interesting shapes. So mark them as such. These are the secondary eclipses. These are the primary transits, because these are just a little bit deeper. Again, done and talk. And I'm not going to waste time with the comments again, but I'm going to keep doing it off screen. So here we have another eclipsing binary, though it may not look like one because it looks from afar like it's a pulsating star. But if we zoom in, you can see that um, you can see the primary transits and it's alternating dips. So got a smaller dip, larger dip, smaller, larger, smaller. These are the secondary eclipses. These are the primary transits. It just doesn't look like it is one because of how fast or close these two objects are together. Normally I would mark all of these, but it is a lot of transits. You'll be here for like around probably 3 to 4 minutes just putting all the transits on. So it's not entirely necessary in this case. And the comments I make for this subject will be very close / contact eclipsing binary, because sometimes eclipsing binaries they do touch each other. The photospheres almost merge in a way, but they're spinning so fast that they don't actually um, converge into one body. And if you want to see more eclipsing binaries and what they would look like, then I'll put a link to the collection that I have of them in the description below. So you can see there's a massive wide range of different types. So here is a body that I've just found. From doing the radius calculation, it looks like it's right on the border between being considered a planet and an eclipsing binary. So to know for certain, we need to check exophop and the TCE. So I'm going to start with the TCE first, and as you can see, the body is 1.67 Jupiter radii, and if we check the vetting report, vetting summary, almost everything is clear apart from this red flag, which is indication that this might be an eclipsing binary. If we go back to exophop, this object has been designated as a TOI, TOI 1635, and if we look at the observing notes here, you can see that an astronomer has found that there are secondary eclipses along the light curve, separated by 8.8 days between the primary and secondary. So this means that this object is an eclipsing binary, and therefore is being ruled out as an object of interest and is false positive. So the comment I would make for this is mentioning where the transit is on the curve, the fact it's a TOY, and then a link to exophop to show it, the TCE and a link to that classifies as a false positive and is therefore an eccentric eclipsing binary. So add that comment and there. So here is another object on the planet binary boundary. You can see that someone has already made a comment linking us to the TCE, informing us that it's already a TOI. So when we look at this TCE, we can see that it's a slightly smaller object compared to the previous one we looked at, with a Jupiter radii of 1.4788. The vetting summary for this one is all clear. Everything looks good. The centroid's all good, and you can clearly see the transits right there. Another helpful tip to tell the difference between planets and binaries is the shape of the transit. U-shaped transits like this one, they tend to more often than not turn out to be planets. And if they are V-shaped, so if there's a shape like a V, then it will be classified as an eclipsing binary. Though it's not always the case, so don't take the shape of the transit for granted. And so on ExoFOP, you can see the astronomers are really interested in this object, which is also a good sign that this is a planet. As you can see, they've allocated multiple teams as a priority 1, and 1 means high and 5 means they're not interested in it or put it in the backlog. So there's a few details about the planet, and because this object has only been found recently, there's not a huge amount of observations, so there's only a time series observation has been done. So back to the talk page. The only thing I would add to this comment is just a link to the ExoFOB page with the TOI number. The Sinbad link to the actual star that's this object is orbiting. So once, if this thing turns out to be a planet, the planet will be known as HD 133725b. And just a couple more notes showing that its vetting summary is all clear. It's possibly a hot Jupiter planet, and that the professional astronomers are liking the fact that they're interested in this, because it's also a variable star. So I think that's what interested them the most. So put this comment in, and I've also added it to my collection of planetary candidates. So now I will show you a few other phenomena that you might encounter when planet hunting. This is a trinary system. You can see that the deeper transits are those of a much larger stellar companion, with the secondary eclipses clear and present. But you can also see there's a much smaller object that is transiting. So from afar, it may look like a planet or something much smaller, but you have to also look at the transit depth, and you can still see it. The object still blocks roughly 4% of the incoming light. So this makes this system a trinary. These are relatively rare, but they are quite interesting to find. Next we have Cepheids. These are characterized by a very regular pattern of a smooth curve that is decreasing and increasing brightness in this sort of pattern. They tend to be that of giant stars. As you can see, this one is 47.6 solar radii. So here we have what's known as a Gamma Doradus variable star. These are characterized by regular wave patterns on the light curve, and these are typical of a very young class spectral type F and A stars, where their brightness constantly fluctuates in this pattern. I've seen on occasion a couple of planetary candidates around these stars, so they are interesting. Now we got the Delta Scuti variables. From afar, they look like they're very close contact eclipsing binaries. but they do not they don't have or exhibit alternating dips. So these are they show very rapid pulsations within a period of a couple of hours. Um, this particular star is what is also known as a SX Phoenicus variable, which is a subtype of Delta Scuti. Um, but this represents stars that are older than normal Delta Scuti stars. So this is a good opportunity to show VSX, otherwise known as the International Variable Star Index. Um, like Sigbad, like Simbad, it gives some information about the target star, but is more inclined to show you details about the star's variability. So here we have the variability type. We have a little window here that shows the description of what type it is and the description uh, of that variability type. Got a few more details. You got the magnitude range of how it changes. Um, we have the first shows when the star was first recorded, which is otherwise known as the epoch, and has the period of the pulsations as well. So this one has roughly one pulsation cycle every 2.8 hours. Um, Also on VSX, you can see the papers that this exact star has been associated with, and a few other, you can see changes to the star and a few other things. So these are what is known as RR Lyrae variable stars. They have this mostly regular pattern of a rapid increase in brightness and which increases to around, well, hundreds of percentage above normal, and then slowly decreases during the day or hours or however long it takes for it to go back to this point down here. And then boom, it goes up again, and this is the pattern it um, shows. Um, these are they are also A and F spectral type stars, but they are different in the way that they used to be red giant stars that have shed mass during a phase of when they were a red giant. Uh, these are often used as tools to measure distances of extragalactic different distances that of well beyond our galaxy, the Milky Way. And from afar, this just looks like another noisy, uh, uninteresting curve. But if you check the subject info of this one, you can see that it's a very small dwarf-sized object with a temperature of roughly 31,000 kelvins. So these are known as hot subdwarfs. They used to be a red giant that was in a binary system, but most of the hydrogen outer layers have been shedded off, and what is remaining is the core, which is mostly helium, which is still continuing to fuse and burn, and which is why this is very so it is still very hot. Um, there's also because there is two different types of hot swap dwarf. There's the spectral type B, which is the one I just showed you, and there's a spectral type O subdwarf, which is much hotter, uh, above I think it's above 40,000 or something, 40,000 Kelvin. And the difference between the two is the O ones usually have um, a carbon oxygen core because they used to be much larger stars. And finally, we have cataclysmic variables. So In this case, this is what is known as a dwarf nova, which is a very long-lasting outburst of matter, which is from a white dwarf star that is stealing matter from its low-mass companion. The result of this as you can see, is a large increase in brightness in the realms of hundreds of percent, but it's a very long lasting in the period of days and weeks before it goes back to a somewhat normal trend. Um, Thanks to this great guy, you can see uh, what they would look like. It's these sorts of stars. So there's the white dwarf, and you can see it's stealing matter from its much larger but still relatively low mass companion star. And yeah, he's done a whole bunch of information here. This is some papers from results from papers from research done on this exact curve. So hopefully now you have a much better understanding of what you might encounter when you are planet hunting, and how to interpret and classify most of the stars in light curves that you'll be able to see. I hope this was helpful to you all, and so thank you for your time.